The KISS principle, for those that don't know, keep it simple, stupid. The more complication that you build into an operating environment, the more we run the risk of having a catastrophic outage. And then there's our friends in the government, whether it's federal or state level, the mandates that come out from the government, lines drawn in the sand. We will be 100% this by then, or we will retire that, or we're not going to burn any fossil fuels. It is incredibly hard with these mandates coming down for operations to keep up with things. We just had a change in Washington, and now what, 65 gigawatt of offshore wind on the eastern coast is in jeopardy of not getting built. We may get SMRs instead. So how are we going to manage the change coming down from the regulatory side, which potentially could change every time there's an election? Same thing, similar to the government side, is the markets, stakeholders. For those areas that are running wholesale markets, when the stakeholders get in there and argue about nickels and dimes and pennies, new market rules come out, and that trickles down to what operations has to do in real time. So that's an increasing problem. It could get worse. You know, people want to build markets for inertia and build markets for primary frequency response and build markets for voltage control. And at some point, how do you implement all these markets in real time? There's also the problem with, you know, data centers, DER, behind the meter resources. Everybody's seeing different challenges. Data centers are building in areas with very low cost. You're not seeing a rush to go build data centers in New England and New York because we got terrible rates. We also are the leaders in having gas electric coordination mess in the winter. So a lot of the challenges and a lot of things that scare operations can be very regionally dependent. And also a lot of stuff in the industry now. If you go to all these workshops, everything starts to become weather dependent. We're talking about dynamic line ratings. We're talking about load forecasting. We're talking about all of the stuff buried on the distribution system now. We're talking about variable resources, wind and solar. So there's a lot of moving parts to all of this, but they're being driven by weather forecast. And operations folks are generally concerned that weather forecasting accuracy is not keeping pace with the dependency. Studying the system, it used to be so easy. I look at the peak hour, I look at the installed capacity of all the resources on the system, and you do an offline study. Life is good. Doesn't work that way anymore because now you have all these variable resources. So you can't just look at installed capacity anymore. What do I assume is my solar? What do I assume is the wind? What am I going to assume with batteries? So the industry operationally is moving into energy analysis, which is now a 24/7 study and not necessarily a single hour, a single point in time. In some areas, the retirement and load growth is far outstripping the addition of new resources. You hear ad nauseum about the interconnection queue is backed up forever. How are we going to get ahead of that? And NERC has highlighted that in their recent resource adequacy report. There we go. Some little diving into some of the detail specifics. Uniform, there's not enough engineers in the world to do the work. I don't know exactly what the problem is, but we're seeing the SMEs retire, can't find replacements. You lose the mentoring, the training, the tribal knowledge being handed down from the SMEs to the new engineers. Everybody's fighting. ERCOT steals an engineer from California, and then California steals from PJM. New England steals from PJM, New York steals from IESO, and round it goes. We're playing a shell game with engineers. We can't get ahead of the curve. And salaries. The industry, power systems industry is losing valuable engineers to developers. I talked to one person who said, I lost my best engineer, went to work for who? Amazon. They literally doubled the salary. We can't compete with that. So salaries in our industry are a challenge for operations. GETS, everybody's heard grid technologies they're going to save the world. Everybody's convinced that this is great. Dynamic line ratings, it's turning out to be more complicated than anticipated. Utilities are starting to ask for extensions on implementation. When do we use dynamic line ratings, right? Is it only in the EMS system? Is it in short-term studies, 7 to 10 days out? Are we doing it in longer-term studies, say 6 months into real time? Not real clear. There's collateral impacts. If I up the capacity of a certain line based on the weather, 20%, what happens to protection systems, breakers, substation equipment? You can't just put more current on the line without worrying about the rest of the equipment that's in series. And again, weather. Some DLR has monitoring equipment. That's good stuff, but others are just implementing it based on a forecast. So now you've got to worry about your accuracy. Advanced conductors, good stuff. Everybody knows some of these conductors now will operate up to 250 degrees C. You can almost double the capacity of some of the circuits by replacing the old conductors with some of these new fancy conductors. Well, that's great, but it's being done to change the dispatch. And what does changing the dispatch do? Well, changes the power system angle across your system. And does that introduce problems you've never seen, specifically stability, voltage, and reactive performance? It also may impact your primary frequency response. If I put in advanced conductors and increase transfers by 2,000 megawatts, what does that mean? I may be running 2,000 megawatts more of inverters at the sending end, and I might dispatch offline 2,000 megawatts of synchronous machines at the receiving end. What happens to my system? There's losses. Voltage control, losses in the reactive sense too. Let's not forget there's Q losses here involved, and how does that affect operations? Protection system risks. We're overloading a lot of equipment. Parallel circuits. I take a circuit that's 2,000 megawatts, put advanced conductor in, and I get 4,000 megawatts on it. What happens when that trips? Where do those megawatts go? So again, there's collateral damage you have to consider on other circuits, on substation equipment. God forbid you have to buy an auto transformer. That's about a 6-year wait and maybe $12 million. So just to reconductor a line with an advanced conductor, you better study everything else alongside of it. Dynamic flow control and these topology optimizers. A lot of folks have seen presentations on that. Well, offline tools, PSSE, PSLF, they don't have models in them. And the EMS system sure as hell doesn't have models in it. And you're going to have to write a healthy $1 million check to GE and Siemens to start putting these things in your EMS system. And what do we want them to do? Are they to increase transfers? Are they for contingency protection? Are they to just allow us to take more maintenance during the maintenance season? So what is the functional goal of this equipment and its optimization? And the scary part is if I have these in my system and a dynamic flow control device is changing the flows on the system, what happens when security constrained dispatch sees that change? And does it now adjust the dispatch? And you end up with 2 devices on your system that are just fighting each other. So there has to be coordination before some of this is put in. Here we go. IBRs, BES, okay. Operations has to do studies with these. So again, the mystery stability models, the dreaded black box that nobody knows how it works. It doesn't work right. It doesn't work at all. Again, in operations, a lot is going to be dependent now on the weather forecast, especially with your wind and your solar. You have IEEE 1547 and all this momentary cessation stuff, and you've got NERC with standards, and we continually see event analysis show that people are not following what they're supposed to do. So how do we fix that? How do we chase down bad actors? Areas with high penetrations, they're seeing problem with their area control error, ACE. The tie lines, it's getting harder and harder, especially if my system has a lot of variable energy and my neighbor does too. And now we're seeing the tie line control becoming much more problematic. How do we address that? No one in operations knows what the hell to do with GFM. Are we going to get them? Where are they going to go? Are they optimized? How many do I have to have online? Are they locationally dependent? Operations is kind of counting on planning. Don't always trust the planners. And then system short circuit strength. Planners work in a perfect world. Everything is available. They do their contingency analysis. Maybe too deep and -1, -1. Short circuit strength is 3, is 2. Everything works fine. In operations, 6, 8 months of the year, it's maintenance season. The system looks like Swiss cheese. Guess what happens to short circuit strength? It may go through the basement. And so how does operations figure out that I'm getting in a bad place because short circuit strength has dropped in real time and I may get some control interactions amongst a bunch of IBRs? Who knows? So what tools are going to be available to deal with that? There we go. Yeah, okay. Batteries, how are we going to dispatch batteries? Most of the operation sides don't really know. Some have been told it's going to be markets. They're going to bid in. We have some history in areas with that, with pump storage. So are they going to play like a pump storage facility? Or are operators going to have control? So the operators knowing what's happening in the next few hours. I have a unit with a tube leak that may come offline. I have a nuclear unit that may go into a loss of coolant event, which means if they don't clear it in 24 hours, they come offline. I will posture my batteries. I don't care what the price is. Everybody charges because I'm going to need you in an hour. I'm going to need you in the morning. How are we going to do that? EMS tools are not tracking things like the state of charge of all these. And if you put hundreds and hundreds of grid connected batteries out there, we're not ready for that in an operational environment. And there's no historical. If I'm doing an outage coordination study for a major facility out that's planned in 6 months, what do I assume for all the batteries? We used to have historical information on resources on the system. We don't have it with the new technology that's out there. And transfers, again, if we're going to start maximizing transfers across our system through any collection of tools, we've got to start worrying about new problems showing up, stability, voltage and reactive. And again, the short circuit issue. Entities are now seeing oscillations on the system. Do we have detection tools? And more importantly, can you predict or tell an operator what to do in a control room? It's one thing to alarm on an oscillation, but what do? What's the problem? Who are the bad actors? And we don't have the technology right now in operations to find that. Load models and data centers. Okay, you heard a lot about that. Well, load model is getting much more complex. What do you use when you're going to do a stability study or PSCAD, knowing that there's this mystery out there on the distribution system? DER, behind the meter stuff. Who does it? Who develops it? Who's responsible for it? Operations just wants a working model. They're not the R&D people that are supposed to be figuring out what the model is. They are an end user. And right now, they're not getting the support they need. Again, have to factor in weather and how is that impacting a lot of the DER and behind the meter. You heard a lot about data centers if you were here yesterday. What does it look like? What's the protection? How does it respond? And how can we dispatch these things? Are operators going to have the ability to take data centers offline or do something with the DER and behind the meter generation if there's congestion on the system or if I'm heading towards a capacity and energy shortage? So there seems to be a kind of a void there. Gaps in the system, well, there's been the age-old, 100-year gap between what the planners study and the models that they use and what operations gets handed to them after commissioning. That wind farm that had 9 megawatt turbines from one manufacturer has turned into less turbines, but they're now 12 megawatt turbines from a different manufacturer, and operations has to study that. There's poor coordination on DER. The distribution folks look at transmission as that great infinite bus out there. It's rock solid. They don't care what their system does to the transmission side. And most EMS systems only model the step-down transformer with a load. There's no distribution. There's no DER. There's no behind the meter. How do we get a better understanding of how those two interact? It may impact load shedding, Everybody out there has some load shedding, either manual or automatic. And what happens as my load evolves with all these resources hidden out there that are variable? And last, again, the compliance with standards for ride through and momentary cessation. Issue of firmness. I have a whole bunch of variable resources on my system, and my neighbor does too. So if I'm buying from them, what am I getting? What's the firmness? Can I count on it when I have an emergency or not? Capacity additions, again, we're losing the battle of having resources on the system. There we go. Protection, operations needs protection data to run stability studies. They have to get it from the transmission owners. There's just no synchronization between tools, products, databases. Operations may be using PSSC for offline studies and maybe using TSAT and the EMS. How do we sync it all? Again, the whole short circuit issue. How do we track that in real time to decide if we are heading towards the cliff? Historical, right? I said we're moving from peak hour to energy analysis. We don't have tools necessarily. Data analytics may not even have staffing. You may have to start adding engineers in the real-time environment to take care of that. You've got all these variable resources that complicate your studies and your historical data. Again, weather forecasting is going to drive some nightmare scenarios. And how do we fix this and make it consistent across tools? I can't be studying a 5-day out with a load forecast that doesn't match what's in real time. So we've got to do a better job of synchronizing a good forecast across the system. Study practices, operations being pushed into probability assessments. No one really knows how to do that in operations. It's always been deterministic. And so where do we do? Who sets the parameters? Who drives the bus? And it's going to be so much more complicated with all these variable resources being involved. Operations is also being pushed into doing PS-CAD studies. It's a foreign tool to operating engineers. They don't usually do it, so you have to take them offline, send them off to training for a week, bring them back and understand the nuances of a very complicated tool. And how do we take care of that? Real-time operations, we need better tools in the EMS and a simulator to train on. Very important. Where's AI going to drive us? Some people are saying AI is going to fix all your problems. I won't even touch that one. But people claim it will. And then there's a push for these remedial action systems. You know, we want to put all these fancy things that if I have a contingency, trips that, trips this, trip that. The West and the US uses a lot of them. The East is scared to death and does not want to use them. Hang wire, build generation. I don't want them on my system. If they misoperate, the lights go out for everybody. And markets, again, how are we going to implement all these market changes? And gas electric coordination is going to stay a problem. We've seen from the superstorms, we're not doing a very good job of getting ahead of the curve. We need the better analytics, better understanding of the loads, of the generation. And how do we model things that aren't just weather? Wildfires, EMP, all of these things that may impact how we reliably operate the system. Considering what's going on in the world, cybersecurity, everybody wants to communicate more. Let's talk to the Tesla batteries. Let's go talk to EVs that are charging. And where do we introduce loopholes where someone can get in and do bad things, the bad actors? Last, alarms are overwhelming operators. If you think of all these concerns and put in an alarm to address every single one, you've added hundreds, hundreds of alarms. We're going to hire another 30 operators to sit on shift? No, it's not going to happen. And lastly, with all these changes out there, what happens to our black start and restoration? So it finally falls apart. And are we going to be able to have the knowledge to put it back together again? So thank you.
Thanks, John. We'll take questions at the end, as I said. So based on John's issue there, I think the question is, does any operator ever sleep? Not how do operators sleep, but John laid out a lot of problems, a lot of challenges that need to be addressed. The next few presentations are going to look at some of those around better assessment and better monitoring and better awareness of what's happening on the system. So we'll start with Vamsi to talk about ERCOT stuff.
Thank you. Good morning, everyone. My name is Vamsi, manager of the real-time operations at ERCOT. My team provides the engineering services to the control room. So we are on 24/7 shift and on-call support to provide the information to the control room or the operators so that they can make a better informed decision. So we work very closely with them. So I'm going to talk about some of the things that we've been seeing in control room with respect to the high IBR penetration and all the stability issues and challenges we are seeing and how we are monitoring and managing those in real time. We have seen this slide yesterday in Venka's presentation. We talked about how we achieved the high wind penetration, high solar penetration, but I want to give a operations perspective behind these numbers. So when we had the high wind penetration of 39 or 5,000 megawatts, so that happened late in the evening when we don't have solar. And the same thing with the solar when we had a high solar peak that happened on a no wind or low wind morning hour. So when we had both high wind and solar at the same time, then we were able to get only 36,000 megawatts across the grid. So it kind of shows us that we have a high penetration. We have the resource mix increasing. We have more and more units coming online, but at the same time, we don't have enough transmission capacity to bring all that energy into the load centers. So when we had I think somebody asked the question yesterday on when we had the high penetration, what was the percentage curtailed, or what percentage of capacity we still had available but cannot be delivered. I looked into the numbers yesterday, so we had another 25% capacity still available from wind and solar that could not be delivered because of the transmission conditions. It could be transmission condition, or it could be because of the spinning reserves that we have to maintain from the base load units. So we also saw this picture yesterday. So we talked about how the grid has been evolving then and now. We saw that, talked about we are in a kind of a electrical revolutionary period where everything is revolutionizing. So the generation is going through a lot of changes, and then load is also going a lot of changes. But when it comes to the transmission, we haven't seen major improvements or changes in the transmission area. So in the generation, historically, it used to be just thermal units. So we know exactly what they're going to do tomorrow, given they have fuel supply. And the load, we know the load is going to follow a traditional pattern, and we can actually predict what the load could be. But now we have a lot of uncertainty added with the intermittent generation. So we have a lot of wind and solar generations added. And no, the battery. So in the past, we were told that energy can neither be stored or generated, right? So it can only be transformed. But now we say that energy can be stored and used later on, when we are in need of it. So we also introduced the battery technology. And the good thing to point with here is, although we are introducing the intermittent generation, we also developed some good tools to be able to forecast what they're going to do the next day or a week from now. So at least in the near term, we have tools that can actually show what they're going to do to be able to better plan for the system. So we know how much additional resources or the capacity we have to procure, or how much we have to resource we have to maintain. So all of this can be achieved with a good forecasting. So these are actually getting better and better, but still there is a lot of uncertainty with respect to the weather. So weather can change, and it may not be always as predicted. So, I mean, if you can predict everything, then we'll be in a perfect world, but the world is always not perfect. So that's where the forecasting things comes. And also the load, we have talked about demand response, the varying load, elastic load, and then the different type of large loads, the data centers. So now load is not only at the distribution, but we also have load added at the transmission level, and the electric vehicles. So they can be eventually added as a mobile generation too. We could have a heavy electric truck which can probably charge or discharge to different points based on the system conditions. So with all of these, we have grid changes coming everywhere, but not so much in the transmission. So major improvement that came in the transmission area is the use of the dynamic line ratings, where we actually try to look at the weather or the temperature, weather impact on the line's ability to carry flow, and then we try to maximize that. And ERCOT has implemented this almost 10 years ago, so we have always had the ambient adjusted ratings on most of our lines, so which helped us maximize the available transmission capacity. But even now, there are no good tools that can actually help us optimize the available transmission. So we don't have good tools to in the control room that can show, you know, how we can best optimize the existing the transmission network to manage the congestion better. So we can do line switching, or how we can do flow redirect to manage the transmission congestion. That's something where we still have to work, and probably that needs to be evolved to be able to maximize the use of the available transmission capacity. And we saw this slide too yesterday on how the load is expected to grow in the ERCOT. Currently, we are at 80 gigawatts or 85 for summer, and then we already also crossed the 80 gigawatt load mark for the winter. So the winter peak also crossed 80. And then in the next 5 years, it's expected to go to 150. So the numbers can be exaggerated, but still it's pretty high. It's going to be pretty high load. And this is what is actually demanding the fast interconnection process at ERCOT. So we have to bring the generation online at the same pace as the load is growing. So if you don't have enough generation to support the load, then we'll be in a very bad position with respect to the control room. So load shed is the last thing that control room wants to do, and then it haunts them when they have to do that. So that's the last position we want to be in. So we want to bring in as much generation as possible, but we also understand that that's going to bring in additional challenges with respect to the stability concern that I'm going to focus on the next few slides. And here is just some numbers. I want to show some numbers on how the generation mix is changing and what we expect to see in the next 5 years. So if you look at the solar in 2021, the installed capacity is at close to 30 gigawatt beginning of this year. And in the next 3 years, it's expected to be double. The same thing with the solar. So we are at 10 gigawatts, and then it's expected to be tripled in the next 2 to 3 years. But if you look at the numbers with respect to the conventional or the thermal generation, we don't see so much in the queue. We don't have a lot of dispatchable generation coming. And that's where I think everybody is actually looking at other ways to be able to better manage the grid with respect to using the grid forming technologies or leveraging the existing technologies to see how we can maintain the stability of the system, even when we don't have a lot of thermal fleet online. So I briefly touched on this part. So with the current interconnection process, it takes anywhere from 6 to 12 months to add a new load in ERCOT. I think it could be different for the large loads because they have to go through more studies. But in general, we need only 6 to 12 months to add a new load into the ERCOT model. And then same thing, 6 to 24 months, 6 months to 2 years to bring in a new generation. But if you have to build a new transmission line, it's not going to be anytime soon. So it takes at least 3 to 6 years to build a new transmission line. So that's where all the challenges is coming in. So the transmission is not growing as fast as the source and the consumers, the source and the sink are growing. So the key stability areas, so if you look at the ERCOT geography, we have the majority of the renewables, the generation is either added in the Panhandle West, or we have mostly in the South. But those are actually quite far away from the key load pockets. The load pockets are in the North, Central, and the East regions. So we have Dallas, Austin, San Antonio, and Houston. Those are the major metroplex in Texas. And those are the main load pockets in the ERCOT. But all the renewable generation is going to the Panhandle West and the South. It's because of the available resources. So they have land and then high wind and no obstructed views for the solar. So the resources require probably, makes it more sense to add it there. But we need to improve the transmission capacity to bring in all of those generation from far away areas to the load centers. So that's where the main challenges comes. the main challenge comes in. So with the increased renewable penetration, we need to look at, we're actually now at a point where ERCOT has a small areas where small pockets or small interfaces where we have been seeing stability concerns because of too much concentration of the renewable generation with not much transmission capacity to bring it there, bring it to the load pockets, and also not enough voltage support. So we are adding units, but not adding shunts or SVCs or any dynamic reactive devices to be able to maintain the voltage in those heavily concentrated IBR areas. So there's no online synchronous generation, so not much synchronous generation in the area. And the other main challenges that brings in with the IBR is the reduced system strength. So we are seeing more and more concerns of short circuit ratio issues in the small pockets, and uncertainty. So as we have more and more renewable generation, uncertainty is the key that brings in more challenges with the way we plan the system and operate the system. And the write-through capabilities is other major things. So we have had events in the past where the write-through capabilities has caused a widespread cascading impacts to the grid. So the write-through capabilities is something that ERCOT is currently working on standardizing those requirements to be able to better maintain the stability of the system. And here is a quick overview of the pockets of the stability concerns that I talked about. So how we are managing those pockets right now, how we are managing the stability of the grid with this high renewable penetration. So we have, as we go through the interconnection process, we have studies that needs to be done during the full interconnection study submitted by the transmission planning team, and then we have internal dynamic stability team that assess the stability issues we see in the planning horizon. And also as we get close to the real time, we also have an operation stability analysis team that looks at the stability concerns as we get close to the real time. And when we identify any issue with any instability, then we create an interface for that pocket, and we call it as a GTC, generic transmission constraint. So we create an interface and then try to see what could be the safe or the secure limit that can actually transfer the flow across that interface pocket without causing the stability concern. So we try to determine those limits and then try to use those in managing the flow or maintaining the flow below that level across those stability concerns. So that's our approach for managing these right now. Because as we see the way load is growing, I mean, we don't want to stop the projects from coming in. We don't want to stop from building new generation, but we have to find a way to manage them, because as I showed in the first slide, the wind and solar may not happen at the same time. We have probably high solar during the day and then high wind at night. So we want to maximize the generation and try to manage it in real time until we can actually also work on the transmission improvements. So, and because of this approach, we are seeing more and more of these stability concerns. So we started with, I believe, 8 GTCs in the past, and then during the CRESS or when we started having more wind generation added in the Panhandle area. But now, as we start to have the solar and then the batteries coming into the ERCOT grid with more and more additions, so we are at a point where now we have 24 GTCs that we maintain in real time. So we have 24 different interfaces that we maintain and try to manage the flow across those based on the stability limits calculated both in the offline studies and also in the real-time online studies. So most of the GTCs are offline, and some of them we are actually in the process of implementing the online TSAT, so moving all the offline studies into the online system to be able to calculate the stability limits in real time. So how we manage this? So once we identify the area of stability concern, we create the interface, and then we try to see what is the secure or the safe limit on that interface, which can actually prevent the stability concern. We determine the limit, and then we use that limit to manage the flow across the GTC using the real-time tools. So we have real-time VSAT, TSAT calculating the limit, and then we have other tools called the Transmission Constraint Manager, which gives the situational awareness to the operators on what all the interfaces are currently doing and what is their expected limit and how far we are to hitting that limit. So they calculate the stability margin, available stability margin for each of these interfaces, and then they try to maintain enough margin to not let the flow in the base case exceed that stability limit ever. So we always try to keep it. We go with the conservative approach. They always start with the monitoring at 85% of the limit, and then they always try to limit it under 95% of the stability limit. And when we have the offline tools calculate the limit, so it's not always easy to look at use a paper printout or spreadsheet to see okay, this is my limit for this GDC, but the limit is actually depending on the system strength in that area. So available the N-1 conditions, when there is a forced outage or an outage in the area, that actually changes what the limit could be. So all of those things have to be assessed in the offline studies. So, and we have to come up with different limits for different predetermined outage conditions. So all of those outage conditions are actually modeled in our EMS system, and then EMS system will actually look at the current topology in the SCADA. So the SCADA standard is every 4 to 10 seconds. So it determines the topology every 4 to 10 seconds, and based on the predetermined limits, it will tell the operator exactly what is the limit for this outage condition. So if there is a forced outage, then immediately we have the limit updated based on this offline analysis, and then operator will be able to maintain the flow. They can run a security constraint economic dispatch to redispatch the generation to manage the flow. And this is going to change when we start adding all these GTCs into the online TSAT. So because with online TSAT, we are not only calculating it for the system conditions, but we're also assessing more contingencies. What if we have this outage? What if we have this outage? So we already have this outage in the base case, but this outage in conjunction with the other one could put us in a more unstable state. So we try to determine all of those in the online using the online tools. So, and that's the main benefit of going from offline to online. Excuse me. Because offline tools, we can only do so many assessments. We can only predict so many system conditions. And to prepare the base case for the offline, we have to make some assumptions. We have to assume, what our renewables could be doing. So we have to assume certain percentage of the renewable penetration, and we have to assume that all the other lines are in service, but we have probably only one outage. But all of those assumptions are a little more conservative. Maybe we go with the conservative approach just to be on the safe side. And then when operators try to manage the flow, they even go with the further conservative approach. So this limits how much of the renewable generation we can get across from the pockets into the load centers. And that's where the online stability analysis will help, because it will actually exactly know what is the current system topology, and it can run those assessments and be able to tell us exactly what our safe transfer limit across the interfaces. And they determine the flow that we have to maintain in the base case to be able to have a N-1 secure condition. And that's what we use. And then once the limit is calculated, then our transmission constraint manager application will give the visualization to the operator on what is the percentage overload, how closely, how much margin we have on the GTC. And then when they activate the constraint to the security constraint economic dispatch, it will redispatch the generation to maintain the flow. And the redispatch could be curtailing the generation behind the GTC. So curtailing the generation behind the GTC and then probably ramping up the other units outside the GTC area. And the offline PSSC studies, like I said, so we are still in the process of putting it on the online. So some of the GTCs are calculated online using VSAT, TSAT, and some are still done using the offline studies. And we hope to probably get all of those moved on to the online system by next year. The challenge with getting all of them to the online system is, like I said, we are currently managing 24 GTCs. And for each GDCs, if you want to calculate the stability margin, we have to do transfer analysis in TSAT. So if you're all familiar with how TSAT does and then how computationally intensive TSAT application is, it has to study the base case condition and then push the transfer across the GDC further and further to see until it gets to the stability point and then be able to send the limit back to the EMS system. So we have, and it has to do that for several different conveniences. For each transfer level, it has to assess all the conveniences. So right now, the only 6 GTCs enabled, in our test system, it already taking like about 5 to 6 minutes. So if you have to run all the full 24 GDCs, then I think it will be at least 20, 25 minutes. So we won't be able to run it as frequently as we're doing now. So we run it every 10 minutes now, but we may have to extend it. But it'll still be better than using the offline limits where at least, we are at least close to the real time. And the other challenge with the online stability is the online tool needs to have the accurate representation of the IBR models. You need to have the accurate representation of wind and the solar models. And also the base case conditioning. So we need to have a good reactive power coordination between the resources and the transmission owners, which is very key to have a good power flow base case, which goes into the assessment. So we have seen issues where a lack of or a poor coordination between the entities have actually caused some stability concerns in the past, and we were actually limiting the flow across the GTCs because of that. So we had extensive conversation with both the TOs and the resource operators and see if there is anything they can do better. Because if the unit is producing megawatts to maintain the voltage of the PY, but if the transmission owner also had a reactor connected, maybe one station away from that, then it's not all the reactive output from the unit is not really helping the grid. It's not helping maintain the stability of the grid. So we have been reaching out to all our transmission and resource owners to do a better job at managing their reactive powers. So some of them already have some dashboards built into their control rooms, and the others are actually working on it where they can see what the units in their territory are doing, and then they are actually helping the units be at their the optimal or the neutral reactive output by leveraging the other reactive devices available on the transmission network. And like I said, maintaining the dynamic models and scenario for the real time is a challenge because ERCOT, I don't know how many of you know, but we update our production network model every week. So the network model changes every week. And as the model is changing, and because of so many interconnection projects, both with the generation and the load, and we have the transmission reconfiguration going on, so it could change the conveniency, or it could change the topology. We may have to probably revisit how we define our interfaces. So all of those have to be assessed as we get more and more of these changes getting into the production system. So all of those has becoming a challenge. So we have weekly or bi-weekly meetings to talk about what's coming our way, because we have to plan for these things. So some of the issues identified during the quarterly stability assessment performed by the stability coordination team, they would actually have a limitation on when the unit can be commissioned, because if they identify any criteria, then first we have to create the GTC, have all the models ready, and then we have to have the limits calculated and EMS model ready for that interface, and then we are in a position to be able to maintain or manage the GTC in real time. So all of this has to happen before the unit can be commissioned. So it requires a lot of coordination. Sometimes the resource is expected to come online next month, but then all of their probably work is done early, and then they want to commission sooner. But we were actually planning it based on their initial submitted target date. But we have to get it sooner. Then it's very hard to do all of this coordination across multiple teams in ERCOT. And sometimes the project could be pushed out. So when the project is pushed out, then we still have all of these changes done in EMS to model the GTC, and then we have to again have plans to not constrain on that interface until the unit is commissioned. So all of the challenges with that we see on the operations side with the increasing penetration. But not just challenges, we do see benefits too. Like I said, the primary benefit would be the more situational awareness. So instead of using the limits calculated in the offline studies, which is done based on some predetermined input conditions and also only N-1 outage condition, but things doesn't happen the same way in real time. So as we have more multiple outages, then we have to go back and do more offline analysis and come up with a new limit to be able to maintain the GTs in real time. But the online assessment will actually help with that. So we can determine the limit in real time or near real time. And this will also help with getting more of the renewable generation across into the load pockets, because we are actually, since we are not using so many conservative approaches, actually, we can actually leverage the existing transmission network and be able to push more power from these IBRs into the load centers. And the main advantage would be we will be, since we can do these assessments in real time, or we can also run the same assessments in our studies, and we can see how it's going to change. Maybe a few hours from now, or maybe at midnight, or next day, or during the peak load next day, so we can see how the stability limits is going to look like based on the current forecasted conditions. Because we have, at least for the next 24 to 48 hours, we have a very good renewable forecast. So we know exactly what the wind and solar is going to do. So we can use that forecasted information and be able to come up with the limits for the next 24 hours, which can be used in our day-ahead and reliable unit commitment tools to be able to bring more generation online, as needed. And that's what my last slide.
Thanks, Vamsi.
Yeah.
All right, so pass off to Jen here.
Sure. Good morning, everyone. So next. My name is Jing Tan. I'm a principal engineer from the National Renewable Energy Laboratory. So it's very happy to be here and share a very exciting field demonstrations of the inertia monitoring in Hawaii. So this is really a collaborative effort with the Kauai Island utilities and inverter vendor called AES and the University of Tennessee, Knoxville. So today I will walk you through what we did there and what we have discovered and what it means for the future of the grid reliability. So let's get it started. And first, inertia, actually, it wasn't really a concern in the past. We have more than enough. But now, because in the past, nobody asked, hey, how much inertia do we have in the grid right now? But now it becomes a big concern. So I want to take the Western interconnection as an example. So as we push the renewable penetration level to 20%, 40%, even to the 80%, if you take a look at the upper figure, this shows you that the inertia actually declined steadily. So what that means? So even with the same contingencies, the largest N-1 contingencies for the WAC system, so you will get a faster drop of the frequency, you will get lower nadir, lower settling frequency, all pushing the grid stability at risk. So for the island grids like Hawaii, actually this will become more severe or big trouble for them, since single contingencies could make the small island grid more vulnerable. And when the mainland grid is still thinking about, hey, how should we handle it in the future? This is the Hawaii is facing right now. So other, island grids like the Great Britain, where Duncan come from. And I think they are already taking actions, and by estimating the inertias and managing the inertias like the Reactive. And it's expensive, as shown in this figure. It cost up to 350 million pounds in a report back in 2021. So the real question here is, how do we can like address the inertia and the stability problems in a way that both effective and affordable. So the game changer here is really how to unleash the capability of the inverter based resources. But however, it's still unclear how much inverter-based resources can contribute. So that's why the inertia monitoring actually is a really good start point for us to understand the inverter's contributions a little better. To understand that question, and we propose a probing signal-based method and to evaluate both system inertia and the inertia from the inverter-based resources. Here is how we do it. First, we utilize batteries in an existing hybrid PV power plants. And we use it to inject a small power pulse into our grids. And we measure the frequency and the power response across the grids at the point of interconnection of the HPP hybrid PV power plants and the synchronous generators, and calculate the system inertia and the inertia from the different devices. So the benefit is there is no additional hardware needed. We just simply retrofit the existing inverters and the plant level controllers to do so. And beyond that, we also refine the algorithms and make it estimate the inertia and the frequency response simultaneously. So this can give us more consistent inertia estimation results compared to the conventional inertia estimation. It took us 2 years to bring this idea to reality. Eventually, we demonstrated this capability from the hybrid PV plants by providing you the power system inertia and quantify the inertia contributions from IBRs. I will quickly share what we have done in the past. So definitely the first step is how to design the probing signal and the inertia estimation algorithms. We grab the models from our utility partner. All the work has been done by the model-based analysis, but we determine the size, the shape of the probing signal in order to make sure it won't bring the troubles when we really implement that in the field. The second step, we still call it the pre-demo de-risk stage. So we build the whole real-time model for the Kauai Island in RTDS. And we tested, conduct a very extensive testing at NREL's Flight Island campus. And we kind of like eliminate a lot of potential risks such by refining our algorithms and refine a lot of things in the controllers, such as we did the kind of like noise impact and synchronizations and the communication issues. Those issues has been addressed. Eventually, we move to the third step, which is the field demonstration in the Kauai Island. We have conducted several short tests and as well as full day testing, continuous testing by implementing this probing signal into the KIUC grids. So next, I just want to share the most exciting part is our field demonstration. And for those you don't know where is the Kauai Island, actually it's a very beautiful island we just visited. And it's on the northwestern part of the entire Hawaii Island chain. And the most cool things about this island is actually it's the home for the first battery grid forming inverters back in 2018. So this has been mapped as that's the IBR4 on this map. In 2022, they have converted the second grid following inverter into the grid forming group, which is IBR1 on this map. So what we did here is we work with our AES partner and we implement the probing signals at the IBR2 part, and we inject the 1.4 megawatts power pulse into their grids continuously here. And we measure, so we actually measure the high-speed data from the digital fault recorder, as well as the universal grid analyzer provided by our university partner, UTK. After that, we calculate inertia. We also send this inertia value back to the KIUC control room and display it there in real time. So I could keep talking about this for over 2 hours. But today I only want to share one important findings. I think it's very crucial when we move forward with the inertia estimation. So let's take this one-day inertia estimation as an example. And this is a simple figures. And the blue line actually shows the estimated inertia we got from the field. And the green line indicated actually it's the nameplate of the synchronous generators inertias here. So we can see the significant difference between the measurement inertia and the benchmark inertia. Actually, this is a good sign. It's much bigger than the nameplate. But when we first saw this, the first question come to my mind is, what caused this difference? Is that because of the inaccuracy of the algorithms, or this is purely from the inverter-based resources or the load? So in order to answer that question, we drive some in-depth analysis, try to understand this variable inertia for the grid. The first thing we have done is we intentionally pick up several scenarios that run in the synchronous generator as a synchronous condenser mode. We collect the high resolution data, and the upper figure actually was showing that here it is. So the upper figure actually showing that the system frequency, that frequency spikes is caused by our probing signals. And then the lower figure is showing the power response to these probing signals that we already have measured. So we also pick up 3 tests here, and the results telling us that our algorithms is fine. Actually, it can give us accurate estimations for the inertia of the synchronous generators with an average error less than 6% if we compare that to the nameplate. So if we assume our algorithms is accurate, so it should do the same thing for the inverter-based resources, right? So could you give a guess? When we move this to the inverter grid forming VSM and the grid forming droop, how it should look like? Here you go. So the left figure is the grid forming droop. The right is the grid forming VSM. The orange line is the traditional inertia estimation results. And the blue line is what we call the benchmark of the IBR inertia. So for the grid forming droop, you can see there is no inertia control block has been built in, but it still provide very good inertia contribution, I should say, in this content. This is only a 30 megawatt grid forming, but it can provide 30 to 70 megawatt seconds inertia to the grids. And when we move to the right hand, it's the grid forming VSM. Amazingly, it provides more than the grid forming droop. And it's even double the nameplate. I think this definitely is a good news for vendors. And that is what we got from our measurement data. But this also poses a very big challenges for the grid operator. As you can see that it's not a consistent value. It varies a lot. Then what does that mean to the grid operator? So the grid operator needs to understand what's this variant inertia from the IBR and how to use it for a real-time application. So our team actually, here I want to share a little bit of insights about why this becomes a variable. It's explainable, but still need the kind of like solutions. So the right figure is showing that how the traditional power grids response to a frequency decline. As we are saying here, they use the primary frequency control in blue, and the secondary frequency control bring the frequency back. And for the inertia, it didn't plot here, but it's a very essential and a critical piece that will help us to arrest the frequency decline before the frequency reach the nadir. This make for the primary field control of the synchronous generator, actually, it's mainly driven by the governors. So for the very first 0.5 seconds, so this kind of like the rate of change of the frequency mainly driven by the inertia. So this gives us the chance to measure the inertia of the synchronous generators accurately. However, when we move to a modern grid here, when we are talking about the faster frequency response, you can see that no matter what type of the, you can name it as the synthetic inertia or the mechanisms like the droop response, droop support, or other controls. It all fall into a time frame of the inertia. So I just want to emphasize that. So that brings the challenges that in the conventional or traditional grades, it's easy to measure it, but now in the modern grade, control matters. So I won't be able to expand that too much, but just want to deliver this message to your mind. That's why this caused the variant inertias. But this doesn't understand it is one way, but it doesn't help us to resolve the problem. So the next question is, how can we make this variable inertia is more useful for the system operator? So actually our team has developed an advanced method. I try to evaluate the inertia and the frequency response by aligning it with the controller's parameters. So the left figure is showing that when we test it in model, so we use a generic VSM model. So this time, the measured or estimated inertia perfectly align with the nameplate of the VSM, which is 80 megawatt seconds. However, when we deploy that to our field data, still, first, the results is better. It's much closer to the nameplate, right? But still see this time varying inertia estimation results. So basically later we find out that this is because of the modeling gap between our generic VSM model and the real control that has been implemented into this VSM. So here the main takeaway message is, so in the future, if we are thinking about doing some inertia quantification for the inverter-based resources, definitely field testing and accurate vendor model is really essential when we're doing the evaluations. And so, at this point, I think I would like to provide you another second look at these results. So by now, we are not only can provide you inertia values or real-time inertia values at a system level. We also can break it down to show you that how much VSM can provide, droop can provide, the load can provide, and a synchronous generator can provide. And meanwhile, I also want to highlight that with the help with the KIUC operators, we also intentionally trying to run a 100% renewable operation from 11 a.m. to 11 a.m. to 3 p.m. So this 3-hour 100% renewable operation, we also can see that it has been supported by both. It's not, you may find a trick here. So even we are running 100% renewable for this island grid, but we're still operating the synchronous generators with in the synchronous condenser mode. So basically here, I think this is still a kind of like an open question for all of us, but I want to quickly wrap it up from two perspectives. So first, what we have learned from a device level perspective, I think we have the good news for those inverter vendors. No matter for the grid forming VSM or the droop-based grid forming or the grid following inverters, we found that it do contribute to the faster response in the inertia time frame through, no matter you call it synthetic inertia or faster frequency response. And this will lead to reduce some inertial needs from the traditional rotating machines, such as synchronous generators, even the synchronous condensers. However, the measure of varying inertia, time varying inertia, actually pose a very big challenges for the grid operator and planners. Basically, we need to understand how to use those numbers in the system operation. So this leave us more questions from a system perspective, because we know you got a measurement there, you definitely got the data or value there, but it's more critical to understand first how accurate it is and what does that value mean. And meanwhile, how to develop this critical inertia floor for the grid operation for 24 hours, 7 days. So this, meanwhile, I think it's, in my mind, it's more important to revisit the concept of inertia and refine those inertia monitoring algorithms and develop a deeper understanding about the system inertia. Because in traditional grids, the power system inertia, we always think this is the rotating inertia from those physical mass. But for the modern grids, power system inertia actually depends on how we define it. If you, from the different perspective, energy balance perspective, you can get totally different things. This is a call for the new matrix, new method to help the system operator and the planner to determine where and when and how much different type of the faster frequency response of the IBR we may need for the future or current modern power system. At the last but not least, I would like to thank all the great work that my team has been done for this field demonstration. There's tremendous work that they have been put into this effort and make the field demonstration successful. Yeah, I also provide some publications from our team and for your further reading. Thanks.
All right, again, hold the questions to the end. Last speaker is Duncan Burt from Reactives.
Great stuff. Thanks very much, Aidan. And what a fantastic morning of presentations. Like, for me, huge congratulations to ESIG for everything, for putting these sessions together. It's been absolutely superb so far. Hopefully I can live up to that too. So, John, I loved your presentation. So I used to, before Reactive Technologies, I used to work at National Grid as the system operator in the UK. And I miss that find the problem mindset and that constant, if you ask, have you got any problems? Yeah, I give you 100 problems. So hopefully I can give you some navigation around some of that, John, as well, because there's something really fundamental here. You know, as you've seen in all the presentations this morning, the grids are changing. Models are really important and they can get you so far, but those grids are operated and planned by people who have 10, 20, 30, 40 years experience, yeah? And this is not all science. Some of this is art, it's learned practice, and you've got to intervene in that virtuous circle of understanding what's happened, going back to it, reviewing, setting policy, determining frameworks that the control room should then run in, the planners should then run in, and then training and implementing into those frameworks. So I'm going to talk about how some of all of that fits together. First of all, a little bit about, wait, which one am I pressing then? Oh, okay, sorry. So Reactive Technologies, we're a rapidly growing company. We do measurement of some of the critical parameters that you become really, really important, that John starts really worrying about and Vamsi starts planning for when you've got a high renewables grid, and that is inertia. Although if you want to spend 5 hours with Jin and I talking about what inertia really is, you can probably join us later. But we call it inertia because that's what everyone calls it. And system strength, which again, we can do another 5 hours on. Most of our customers start at short circuit ratio or short circuit level, and then work up from there into voltage stability and synchronous damping and everything else. So we measure all of that, and we measure oscillations because you want to know what's going on the system. Yeah, that's rule one, is you should understand how your system is behaving not just what your models and planners told you 3 years ago. As a side note, John, we used to have a team of 10 people whose continuous job was to, we called them gap closers. So they took the model from planning every week and then reviewed how the real system had been different. And even after 20 years of continuous operation of both those models, it took 10 people every week reviewing that to figure out where the gaps were and improve it. So, you know, once you get beyond the connection queues, you know, you've sorted that bit out and you're just into them planning and operating the system. What are we seeing around the world with our customers? I'm not going to go through all of this because a lot of you will know it. Accurate modeling of multi-IBR systems, big issue, and that's even before you put grid forming on it. And everyone is doing new modeling. We saw Hussein this morning with some of the EM2P stuff, which is fantastic. That fundamental change in system behavior, again, John touched on that. And really, we, you know, as operators and planners, we need to rapidly build that experience that's been accumulated over the last 30, 50 years, yeah? So that is all about much greater awareness of what's going on in the system, more analysis of it, more review of it, and more monitoring. All of that increased variability and flexibility, again, John talked about in terms of adding in whole new dimensions of complexity into the operational environment and the planning environment as well. You know, we can have loads of slides with equations on, but fundamentally, some of this is simply about control room training, new tools, and forecasting. And in the UK, we established an additional shift team and spent millions of pounds upgrading all of our simulation facilities so that you could push 2 to 3 years of authorization training through an extra ton of people and build that capability much, much faster. You know, I've seen one slide on that for every 200 slides I've seen on grid enhancing technologies and stuff like that, but both are equally critical in the mission to deliver a very reliable high renewables grid. There's an awful lot in here about new standards and policies which needs to happen as well. And I'll talk about a virtuous circle around that in a minute, but John said it earlier, he goes, what the hell do I do with that? Yeah, you've got to have, you know, that is 2 years of meetings to argue over what the policy and the standard should be, so that then someone can train for 3 months the people in the short-term planning and the control room to then be able to do something that someone's decided is okay. You know, and that's only if that all works and you put it up to the executive 3 weeks before you're going to implement it and they actually say that's okay. If they say they don't like it and you have to start again, then that's another 2 years. Yeah. So pragmatically, some of this takes a lot of time and it's got to be based on planning and modeling and real data and experience as to how the system is behaving. And behind all of that is really, really significant investment, expansion of people and teams and capabilities and everything else that we need. Sorry, that was a long intro. Right, so what are we seeing technically on systems around the world? The first one is that frequency behavior on every power grid in the world, particularly those with renewables on, is becoming increasingly localized. Just going to let that sink in. Yeah. This idea that, you know, in terms of controlling the variables that you need to worry about in your model, that you can go, okay, well, look, I'll just assume the frequency is the same everywhere. Yeah, it's not. The frequency, if you have a big event on the grid, like a power loss, that transient, that dip in frequency travels like a wave across your power system, hits the edge and bounces back. And that wave, just like a water wave in the sea, contains energy. Yeah. And that energy moves across the system with the wave. And if it gets to a bit of the system that's weaker, that wave actually gets bigger because it's still got to carry the energy through it. So there are lots of implications of this, and EPRI have done some work looking at the WEC and the behavior of frequency on the WEC. There's lots of other studies. We've got tons of data within our systems on this, but it means that, firstly, as Hussein's demonstration showed this morning, the response you get from your frequency response providers will be different in different parts of the system because it's related to the local transient, and it will only happen when that frequency transient arrives. So if your system is 1,000 miles across, yeah, and you have the power loss at one end, the frequency response there will start responding within 500 milliseconds. Meanwhile, that frequency transient is only halfway across the system because it's traveling 500 to 1,000 miles a second, yeah? By the time the frequency transient arrives at the other side of the system, the frequency response here has already responded, and that transient's now coming across the system as well. And then this one comes back and they overlap. Yeah, this is not a simple frequency is the same everywhere. If you take an average of the frequency across the system as an output of your model, that'll tell you the frequency is fine. If you actually look at the frequency at each node on the system, it's going to be completely different everywhere. Yeah? And that mindset shift, if I could give you one thing today, you need to remember that the frequency is different everywhere and increasingly localized. And John, I know that adds to your headaches, but like you're just going to have to live with it. To cheer you up, what we see globally is that frequency behavior is more extreme, i.e. transients and rock-offs are much tougher in weaker parts of the system where there's reduced synchronous damping, and at the edges of systems, like in peninsulas of systems. So for example, New England, or, you know, the top of the work up in Alberta. Those systems experience the sort of full thrust of the wave coming through and then the reflection back off. Second thing we see globally, significantly reduced damping, obviously. And quite a lot of people talk about this in terms of plant retirement, but actually you guys all know the main thing is reduced plant operation. So if that plant is not running, you're not getting the synchronous damping for it. So you see a fundamental change in the behavior of the system. And that's really important. You know, the US is really North America is the capital of studies on oscillations and the behavior of oscillations on the system. As you reduce damping, you know, a lot of those traditional oscillations that we're used to that are forced, actually, they're still there when people make a mistake or they code their system wrong. But what we see much more of in places like the UK and Australia is effectively the arrival of ambient oscillations, where you've got lots of active controllers all talking to each other. The system, related to its impedance and the machines on it, has a natural resonance, which you can see all the time in the frequency, and they just start talking to each other, you know? And sometimes that just goes wrong and you get an oscillation off the back of it. For every one big oscillation, you will find in the data hundreds of micro oscillations, which are telling you that you have an increased risk of a main oscillation. So John, in terms of who the hell's going to tell you when this is going to happen, if you're seeing those micro oscillations, fractions of a second, and you see them when you've got reduced damping, you can exactly tell a control engineer when they're going to have a problem. And you can say, well, if you've got that now, you know, when that gas plant isn't running in the summer, you're going to have a massive problem. Yeah. So you can start to predict this stuff by layering components of data. We've seen it talked about a number of times. John mentioned it. It's mentioned this morning in the grid forming one. So increased problems with voltage stability. We've seen this on the ERCOT system as well. You know, linked to the fact that most of this is IBR running, and you've got reduced short circuit level associated with that. So we provide continuous measurement of short circuit level at a substation based on small voltage probe into that substation as well. Really, really important. And as Vamsi said earlier, you've got this challenge that, you know, you're updating your model every week to try and reflect what's going on. A lot of that model is black box IBR. So actually, you know, really good idea. Let's use some real data, compare what's actually going on the system in terms of short circuit level with what the model tells us should be happening. And you can always tweak the model so that the fault level in the model is the same as the one you're getting on the real system. And you can feed that real-time short circuit level into your online security assessor so that you then know that at least the starting point is the real fault level that you're seeing on the system. Again, there's 5 hours of discussion around how IBRs respond under different conditions and what that is, but that's for later on. Next point, and there's probably a whole Q&A session on this. Fast control, grid forming, and very fast frequency response, so sub 2 seconds, typically 500 milliseconds, is brilliant. And as Jin said, plays a major role in containing these issues. But you know, you've got to start thinking about the power system fundamentally as an oscillatory system. Yeah, it's like a physical system that vibrates and has its own resonances. What we've seen in a number of locations is this fast frequency response actually can create its own oscillations because you're putting a fast, high gain controller onto a weakly damped system. Yeah. Someone said earlier that we don't see any evidence yet of grid forming devices causing issues around the world. I think if you're a regular reader of grid operator incident reports from around the world, then you will know that that's not the case, and there are quite a few reported incidents of oscillations and harmonics related to damping control on grid forming as well. Certainly, I've read them all. So these fast control devices are incredibly important and valuable, and will be the fundamental underpinning of high IBR operation. But you really need to understand how your grid is behaving, understand the natural resonances in it, understand the time constants, and that is, someone mentioned it earlier, hardware in the loop modeling, multiple grid forming controller modeling as well, all really, really vital. But the frequency is not the same everywhere. Yeah. So you can't just put the controllers next to each other and go, oh, it works, that's fine. You might have a 200 millisecond delay between the signal leaving one controller and arriving in another. You've got to replicate a fully complex system. That's only possible to a certain extent. So some of this you've got to do by experimenting, by gently introducing this stuff onto real power systems. So to the conversation with IESO earlier, like I would definitely think about, flicking one of those grid forming inverters on early to see how it behaves, and just get used to that as part of the innovation trial, and people around the world could be having a go with that. And the development of those standards and everything that becomes vital from a measurement point of view. So then very quickly, what are we doing? My fundamental message is that no one in this room would dream of operating a grid without measuring the voltage and current on that grid, would they? Yeah, so why would you try and operate that grid without measuring the inertia and system strength on that system? Because they, as you've heard this morning, become critical security parameters for that system. So very quickly, the sales pitch quickly here. So we offer all of this within Grid Metrics, which is a system based on sensors and some probing modulation, which allows you to measure inertia, system strength, oscillations, and a whole load of analytics around that. Very fast to stand up and turn on. Quite similar in some ways to the system Jim was talking about that NREL had deployed in Hawaii. A few observations just to give you a bit of a feel for some of this, because there is really a virtuous loop around how all of this works. So what I'm showing you on this graph is some of the data from the UK, and what you can see is the residual inertia that's available, that's coming from load, not from generators, but from the load on the system, so synchronous fans, motors, pumps, etc. Key lessons from first deployment in the UK is that some of the declared H constants from generators will be inaccurate. Yeah, that's before you get to grid forming, Jim. And that the inertia that you get from load really varies significantly. And if you start measuring it, you can really improve the forecasts that you've got and include that component within your planning and then into your operations as well. To give you a little bit of an example about what that looks like. So these are 4 population groupings of how the inertial load on the UK system, on the GB system, behaves. And you can see that they have different, on the right-hand side there, you've got the day of the week, Monday through to Sunday. And you can see that different behavior shapes dominate on different days. And that's because in the UK, most of that inertial load is coming from either from sort of light commercial and some industrial, or from water pumping and a couple of other components. If you go to the Australia power system, that's got lots and lots of mining activity on it, you see a completely different set of load profiles for the inertial load on the system. In the UK, that inertia from load makes up typically 20 to 30% of the inertia on the system. If you go to Australia, that inertia can make up 40% of the inertia on that system. But a lot of it's coming from mining, which is hundreds of kilometers away from the demand centers in Australia. So again, presents a different set of challenges around how you manage voltage, synchronous damping, and stability. But it at least allows you to put that fundamentally into your models, whether you get them from Hussein or anyone else, that then really allow you to understand how the system is behaving dynamically and what the frequency is doing in millisecond time frames at every different point on the system. And I want to just finish off quickly with this. This is the virtuous cycle that we're in and really which ESIG drives. Yeah. Because nearly every customer says, well, okay, you've got some measurement data. Sorry, I've got some measurement data. Well, what do I do with it? And the thing is, and I always say about, well, what do you do with your voltage data? Yeah. You use it in everything that you have to plan and operate the system. And the challenge is that you've got to decide how you go into that cycle. Yeah. So the first thing is that it really tells you what's going on the system. Yep. It allows you to hone and develop policies and standards for rock-off, nadir, for fault in feed. That then allows you to do forecasts and develop all your training plans and delivery plans for operation. That allows people to understand that measurement data, lets you understand whether you're operating in that way in real time. And then, of course, you should also do a massive amount of event review to understand what's working and what isn't, identify issues with all that data, and then feed it back into refining and developing more policy. I've left this final point in which summarizes everything we're seeing on, but I'll leave that just for the pack for people to have a look at later. And Aidan, I'll pass back to you.